So what we'll talk about today is GE in contrast to other longitudinal methods, so where it fits, how it's similar, how it's different, specifying the distribution and the correlation structure in GE, looking at time as a continuous predictor versus a categorical predictor, and then just interpreting the intercept and slope effects, so interpreting the output. Before we move into that, who ran some moderated mediation last week? No. Yeah. Any questions from last week? Okay. All right. Oh, and then the reading. What is in the folder for this week? What is in there is like a GE 101, a nice brief paper on kind of distinguishing GEE from MLM, and then there's a paper on testing mediation in the context of GE. So 3 good papers for sure. Oops. All right, so in terms of last week, conditional indirect effects broadly encompass a range of greater than 3 variable relationships, where the presence or the magnitude of one or more of the indirect effects or the mediating effects are conditional upon a specified value of one or more moderators. So last week we talked about one moderator, but you could have more than one. Moderation at the A or the B path, 2 moderators at the A path or the B path, etc. There are many scenarios for this type of model, but generally moderation occurs at the A and or B path of the mediation chain. And Preacher, Rucker, and Hayes, which is the paper that we really focused on in learning moderated mediation, describe 5 different models, that kind of 5 different forms that conditional indirect effects can take. In terms of power, running power analysis for mediation, this is an area that's still developing. There are some programs and macros out there, but also, as I said last week, that I've had good luck just using power tables and describing a range of effect sizes for an A path effect versus a B path effect, and different combinations of magnitude for effect at the A and B path in determining power based on a table. And then we briefly touched on extensions, so thinking about SEM, longitudinal SEM, multi-level mediation, and then briefly introducing causal modeling. Okay, does that all sound familiar? All right, so GE. So why use GE? Why not just use repeated measures ANOVA? Well, GE definitely is a more flexible approach than repeated measures ANOVA. It has more flexibility and capacities. So some of those examples of those are that ANOVA assumes categorical predictors, so GE can have both categorical and continuous predictors. ANOVA doesn't handle time-varying covariates, so ANOVA will give us, repeated measures ANOVA will give us a time-varying outcome, but only a static predictor. So in GE, we can have both time-varying independent variables and time-varying dependent variables. It's not necessary, but it's an advantage if those are the type of models that we want to run. In ANOVA, the ANOVA assumed treats time as a categorical predictor, and so what that means that it assumes that everyone is measured at the same time point, and that that time is in equally spaced intervals. As far as missing data is concerned, you either have to impute it or it's listwise deleted in a repeated measures ANOVA, and in GEE. The GE will maintain all available pairs of data, so as long as you have 2 observations for a given case, then that case will remain in the model, and that case will contribute information to the model. Just going back to time is categorical versus continuous. The difference with GE is that when you can treat time as a continuous variable, it means that you're able to have unequally spaced intervals, like say month 0, month 2, month 6, month 9. You're also allowed to have people coming in at different times. So say like you had a longitudinal study and you know your second year follow-up, some people are coming in at month 12, some people are coming in at month 15, some people are coming in at month 18, etc. GE will accommodate that. And then finally, repeated measures ANOVA assumes an equal correlation between observations over time. So that's what's called a compound symmetric correlation structure. And that can be fine. But the advantage of GE is that you can be just a little bit more sensitive in how you assume the relationships between adjacent observations are. So time 1, time 2, time 3, times 4. Is there an equal correlation between 1 and 2, 2 and 3, 3 and 4, etc.? 1 and 4, etc. Or does maybe the correlation diminish over time, or does it increase over time, or you know there's other variations besides that, but that might be more realistic to what we're thinking. Like in a treatment trial, we probably would think that the correlation between time points would diminish over time because more life is happening, right? Does that make sense? Any questions on that? So this is just looking at a wide data set. So in ANOVA, we work with a wide or a cross-sectional data set, or it's also called an unstacked data set. So this is an example where you have 4 time points, and then you have 6 cases, right? And then it says, so it's time 1 through 4 and chem 1 through 4. In this case, chem is the independent variable, and time is the score on some dependent variable measured at 4 time points. Okay, so here you have a time-varying predictor and a time-varying outcome. So this is just some simple code for flipping the data. So who's flipped their data for longitudinal data sets, moving from a cross-sectional to a longitudinal data set? So some of you, not all of you. Okay. So when you want to do GE, the first thing you have to do is flip the data from cross-sectional wide data set to a longitudinal long data set. So here's an example of SAS code. Here's an example of SPSS code. So the new data set we could call long 4. The set that we're reading in we can call wide 4. So that's there and there. In the SAS example, time we can add on time as a continuous variable. So here we have time 0, 2, 3, and 6. And then score, which is the dependent variable. So this is, we're creating the score variable, which is the score at time 1, time 2, time 3, time 4. And then the chem variable. So creating those single variables that have then multiple observations. And then SPSS, it's pretty similar. The command is called variables to cases. And you have this make command. So you make chem and you make score, just like you did up here. Here there's an index 4, so it's going to create a time 1, 2, 3, 4. So you would actually recode that into 0, 2, 3, 6 in a separate step. So that's not shown here. And then these are the variables that you're going to spit out, plus the index variable, which is the index for time. Make sense? Okay. This is what it'll look like. So now we've got 4 observations per 6 cases, right? We also have that time variable that's 0, 2, 3, 6, and then the score and the chem. Okay? So that's what the long form data set looks like in contrast to the wide data set. Any questions on that? So this is just thinking about the difference between a GE model and a linear regression model. So at the top we have our familiar regression equation, the mean predicted y, which is equal to the starting point when the predictors are at 0, the intercept, and then the slope effect, and in this case, the same example we're working for chem, the slope effect for chem plus error, right? The difference with the GE model is that we have this range of scores for the dependent variable, and in this example, we also have a range of scores for the independent variable, although that's not necessary, right? And then we also have this time predictor, and then we have an adjustment, a weight adjustment that for the assumed correlation structure that we kind of impose on the model, plus error, okay? So if this were a multi-level model, the difference here would be that these would be modeled rather than kind of fit, right? Well, actually, in a multi-level model, you would do both. So you would assume a certain correlation structure, but then you would also model the random intercepts and slopes, right, across individuals. So this is just thinking about those differences a little bit more. This is just kind of showing us that, like, starting with a linear regression or a linear model, we're talking about linear regression, ANOVA, and COVA. This assumes that the responses are independent. So if you had a cross-sectional longitudinal data, like the wide 4 that we looked at initially, you could run a regression model on that, and it would give you 6 times 4, you would have 20, it would treat it like there were 24 cases, and it would think that those cases were independent observations. So that we don't want, right, because they're not independent observations. The only difference here is that the distribution is generalized, right? So now we're generalizing to different distributional assumptions, like a logistic regression, a Poisson regression, negative binomial, etc. Still, we're assuming responses are independent. Bless you. In GEE, we assume responses are correlated, right, which is closer to reality. And but we sort of fit or impose the correlation structure that we think is happening between the observations. In a linear mixed model, or a multi-level model, or a hierarchical model, or a random effects regression, however you like to call it, responses are also correlated, but the correlation is also modeled to a certain extent by the random effects analysis, okay? And then the difference here is just now we're just generalizing the mixed model. So that means we're extending it to that wider range of distributional assumptions. Okay, so in both of these, well actually 1, 2, 3, this is, we can change our distribution if we want to, right? So what does it mean? And I've wrestled with this, and so if anyone wants to add on kind of, this is how I discriminate the interpretation of the two, I would love to hear it, because I feel like I don't totally have a satisfying way of describing it. But in terms of the differences of the inference, we have a subtle difference. With GEE, it's a population average inference, and what that means is that the analysis describes differences in predicted mean y-scores across the population, right? So we're looking at between person effects, right? And those between person effects give us interpretations about populations, about depressed people, about men, about women, about people who get control versus people who get treatment. This analysis is informative from a population perspective. This could be for policymakers or even providers desiring to optimize outcomes across a population, say depressed individuals. In terms of mixed models, it's a subject-specific inference. So the analysis describes differences in the predicted mean of y conditional on the patient-specific random effect. Okay, and said another way, these are differences within person from a population characterized by the averaged random effect, right? So it's the averaged within person effect. That's the part where I get a little fuzzy, because, you know, the difference between an averaged within person effect and an average between person effect is hard to think about to me. Because if hypothetically the within person change could be a between person. Okay. So anyway, this would be most relevant from an individual patient's perspective. So let's just say it one more way. Parameter interpretation in GE versus MLM. The parameters in an equivalent MLM versus GE model. In GE, these are expected differences within the population. That means given a change in everyone's X from one value to another, and conditional upon the intercept and the adjustment for the correlation structure. Versus an MLM, this is their expected differences within the individual, and it's given a change in their X from one value to another, and conditional upon that the average random intercept, so the average intercept across individuals. Okay? Does anyone want to add to like how they think about the differences between the two? Do you guys have preferences for one over the other? Like, oh, I like thinking about within person differences. I like thinking about between person differences. No? Okay. I like thinking about between person differences, personally. But I do a lot of treatment research. But I also do a lot of within condition analysis, so then that is more about within person. So, okay, just any questions on that? The to GE or not to GE, that is the question, is a good little article that also talks about it. It talks about the difference and when you might choose one over the other. So in terms of standard error estimation, like I said, GE allows different working correlation structures. Each correlation structure will be used to create weights for a weighted regression model, right? When deriving inferences from the coefficients, though, it calculates two standard errors. It calculates the naive standard error, which assumes that we are correct in our assumed correlation structures, such as if we assumed it was compound symmetric. If we assumed it was compound symmetric, that would be the same as a repeat of measures ANOVA, right? That basically it's an equal correlation over time. The correlation between adjacent time points doesn't change. Versus a robust standard error, which is the default and which is what we report, does not assume that what we imposed for the correlation is necessarily correct. So it's probably adding some additional kind of adjustment weight there. So the G in GEE means that you can specify your distribution, right? So you have that capacity in terms of a continuous linear model versus dichotomous outcomes, count outcomes, or negative binomial, zero inflated models, etc. And you can choose your working correlation structure. So it is the case that GE is pretty robust to the wrong choice, and the way you can find that out is by running the models a couple of different ways and seeing if the results change based on how you specify the correlation. But the choices are independent, which you wouldn't choose because that's like regression. Exchangeable, which is that it's like EX something like that for the command. But that's compound symmetric, so that's the equal correlations. Autoregressive is one correlation that then is exponentiated, so that's where your correlation is going down over time, right? M-dependent is where you'll have a certain number of correlations between adjacent time points fit, and then you will assume that the rest are independent. So you assume the rest of them are 0. And then unstructured is, it will fit the correlation structure for you, okay? The goal is to find the simplest structure. When I say simplest structure, it means that you want to use, depending on your sample size, you would want to potentially minimize the number of parameters that you have to estimate, right? That fits the data well. So this is an approach where we can compare model fit, right? So that would be another thing that you could do is you could run, say the simplest, like an exchangeable or an autoregressive, and then run an unstructured, which would be the most complex, which would use the most degrees of freedom, and then see which one fit better and see, the differences, potential differences in the results, and then potential differences in the model fit. Okay, make sense? All right. So this is just looking at them. So independence. This would be that would look like, so no correlation. Versus exchangeable, this is going to cost 1 degree of freedom because it's going to estimate only one correlation. It's going to be the same for the entire matrix. Versus autoregressive is also only one parameter estimated because then you just add an exponent, right? But like I said, it's decreasing. Decreasing over time. M-dependent. This, say, is, for example, 2-dependent. It's going to fit correlation 1, correlation 2. These are considered dependent, are assumed to be dependent observations, and it will fit the correlation for us. And then we assumed the rest further out to be independent, so 0 correlation, okay? So you could specify, 3 dependent, 4 dependent, 5 dependent, depending on how many time points you had and depending on what you thought was going on. Mm-hmm.
You can say how many M there are in set.
Yeah, yeah, exactly. And then unstructured is going to fit all the correlations for you based on the data. Okay. Make sense? I tend to use AR1, autoregressive. Sometimes I just use compound symmetric. Sometimes I use unstructured. I don't know, does anyone have preferences with their correlation structure? Their favorite correlation structure? Yeah?
I've seen autoregressive used a lot in my smoking cessation research just because it makes sense.
It makes sense.
That's what it actually looks like over time, that adjacent points are always more correlated than further.
Exactly. So if you think like in a treatment study, you would think autoregressive versus maybe an EMA study, some type of longitudinal study where maybe the time points are closer together and you're not doing any sort of stimulus, then you might think compound symmetric. Make sense? Okay. All right, so here's an example. This is an example I did with Chris Kaler. And so this is a GE example, but it's actually also an example of some kind of fun coding stuff and ways to play around with time. So this was a naturalistic longitudinal study of college student drinking. And all of the students got bi-weekly assessments, bi-weekly online assessments, so maybe a 5-minute online assessment. A portion of them were randomly selected and then randomized into getting an assessment versus no assessment. And so this was a sort of embedded test of assessment reactivity. So the question of interest was, does drinking change in response to just your sort of typical baseline assessment versus, baseline assessment plus some type of treatment. There was no treatment in this study. In the study, we pulled out, so it was like a 2 or 3 year longitudinal study, but we pulled out 9 biweekly assessments, and we anchored them around the report of an alcohol-related event. And this could be even puking, or passing out. So meaning that it's an alcohol-related event, but it's essentially a consequence, not necessarily like a huge event like getting in trouble, etc. So we anchored them around this self-report of an alcohol-related event that came in from their online biweekly assessment. And so one of the coding methods that we used was that we had a -2, -1, which were the pre-event codes, a 0, which was when the event occurred, and then 1, 2, 3, 4, 5, 6 was the post-event time points. Right? So this is an example where you've got time as a continuous predictor because people's events are happening at different times, right? So this was used to examine both event reactivity and assessment reactivity. So we were interested in both and also whether or not they interacted, right? So the assumption is that heavy drinking would go down in response to an alcohol-related event, some type of consequence. So it would be that naturalistic kind of, oh, I messed up, and so I'm going to change my drinking for a period of time. But that there also might be a synergistic effect with an assessment, so that if they had an event and they had that longer in-person assessment, that they might change their drinking even more because the assessment would make the consequences of the event more salient because they have to talk about it. Right? But the assessment was like 1 hour, and it was designed to look like a typical baseline assessment. But like I said, it was in person versus just that sort of 5-minute online self-report. So here's the code. This is the SPSS code. So here's the command. It's under the generalized linear model command. The dependent variable is number of heavy drinking days. When you have a by statement, that's a categorical variable. So the categorical variables are sex, race, and this is white and multi-race. And the reason we combine those groups is because they had systematically different and higher drinking patterns than all the other groups. And then I2 condition is the assessment versus no assessment. Order descending, that's just saying, for a categorical predictor, what's the reference? What are you comparing to? Right, so this is saying descending, meaning comparing higher to lower. With time 0, that's the with statement is where we put our continuous covariates. Here's our model statement, right? So we've got all the controls, and then condition, time 0, condition by time 0. Distribution normal, so which is just a regular linear model. There's your estimation method. I think you can switch it to maybe one other thing, but not like full, I think restricted. I think a REML, you can do a restricted maximum likelihood, but you can't do full information maximum likelihood. That would be switching over to MLM. Within subject variables, here's where we're plugging in our correlation structure, so compound symmetric in this case. This is just a default, the robust standard error. And then this is dealing with missing data, and it says exclude, but really it should say include. In this analysis, I think they were excluded, but this is the default, and you should change it to include, and that's going to keep all available pairs of data. So that's going to maximize the information used. Here's just the same thing, but with SAS. So say React is the name of the data set that we're using. Here's our model statement, so the same model statement. Here's where we're specifying our distribution. We're asking for type 3 sums of squares, and here's where we're we're specifying the correlation structure, okay? And that's all kind of annotated in here. Any questions on the syntax for either one of these? A lot of this, I mean, SPSS plugs in like tons of, this is just like default information. I didn't write that out. Okay. Whereas SAS hides the default information. So, next we created a variable, well, we talked about the variable called event, which is the sort of countdown to the event. Oh no, I'm sorry, I'm messing that up. So, this variable is just zeros for pre-event and all ones for time post-event, okay? And then we're adding all possible terms. So we've got the condition, the time 0, which is that countdown variable. That's our main time variable. So it's the -2, -1, 0, all the way up. The event variable, which is going to be 3 zeros and then 6 ones, and then all the possible interactions between them. And what they're asking is, does the heavy drinking intercept differ pre and post event? So that's where we're looking at the event effect, right? Does it go down? Is the intercept lower, negative, post event? Does the heavy drinking slope differ post event? And so that's the event by time interaction. So that's saying, not only does drinking go down on average, but then is there a negative slope effect? Was there a higher rate of change in drinking reduction post-event? Does heavy drinking post-event slope differ by assessment versus non-assessment? Right? So will being in that one-to-one assessment predict a more negative slope in reductions in heavy drinking? And that would be the three-way interaction. Make sense? So fun with time. That's the moral of the story. Have fun with time. So this is SPSS output. Dependent variable, we can see number of heavy drinking days. We've got a normal distribution with an identity link. Here's our subject ID variable, our within subject time variable, our working correlation structure. Okay, so let's just check your model. Is that what you wanted it to be? Case processing summary. This is giving us this is the full number of observations, so it's going to be the available n by the number of time points, which in this case was 9. So you can see we do have missing data excluded. So it was 431 subjects by 9 time points, and you can see that here. This is just descriptive information for your categorical variables. Continuous, here's the descriptive information for your continuous variables. So the dependent variable, apparently this output has added in as a continuous covariate, which wasn't in the code, just FYI. And you've got these fit statistics with a smaller is better criterion, right? So these are going to allow you to compare your models if you say, play around with the correlation structure and to see if you can get a better fit. So here's the output. So the coefficients, confidence intervals, significance, these are the exponentiated regression coefficients, particularly like with if we had a dichotomous outcome, this would give us odds ratios. Okay. So what's the deal? So we've got the sex, race, condition, there's that time 1 audit, time, event, time by event, all the interactions. What's the story? Heavy drinking increases on average pre-event. So that is event effect. Actually, not time effect here. there's a non-significant decrease in heavy drinking on average post-event. So that's the time by event interaction. Sorry, I'm having a hard time saying this. Actually here, the event effect. The slope in heavy drinking is significantly more negative post-event, and so that's our time by event. So we've got a negative coefficient that's statistically significant. Okay? So they're reducing their drinking post-event, but event is not interacting with assessment to produce greater reductions in drinking. So they're not reacting to the assessment here. And we thought about why that was.
Which one's number 4 of the?
Here. Condition by time by event.
The one that's 0.556 for the.
Yes.
Okay.
Mostly we thought that that the events themselves weren't necessarily strong enough, or perhaps too variable. But then again, do you want assessment reactivity or not? Let's see. Any questions on that? I know it's a lot to look at. So this is just a little bit of, this is why GE is good. It increases power by increasing the degrees of freedom, allowing for the multiple observations. It also increases power by accounting for the dependencies among the observations, so having a better fit of the correlation structure. It also maximizes the information using all available pairs of data. It is not just for repeated measures over time. That's the only way that I work with it, but it's appropriate for any nested data, so that's just something to keep in mind. Okay? That's it. It's a short one. Any questions? On GE, do you feel like you can go out and do some GE now? I mean, it's not so bad. It's you just think regression with a correlation that I think is right, and then a longitudinal framework. So interpreting coefficients in terms of longitudinal, sort of longitudinal thinking in terms of intercepts and slopes. And when we say slopes, we're talking, slopes for time, say, for example. So how, where they start and then how quickly or slowly they change. Says yes.
So I have a question. On the next to last bullet point, which is about missing data.
Yes.
Do you know of any literature that has compared sort of a good imputation of missing data with what happens behind the scenes during a full information maximum likelihood approach to data? In other words, the imputation, some of which actually do maximum likelihood type estimation.
Right.
Is it simply an ease of use for the user, or does the full information modeling do a better job or a worse job than a good imputation? Do you know anything?
I think Bob Stout is it's on his to-do list, and if you asked him, he would say that the that imputation, you really have to have good predictors. You have, what is the question is what is a good imputation model, and do you actually have enough of the right variables to have a good imputation model? But
yeah, but isn't
but
the same
the
thing
difference
true when you
between
specify
but
full
the difference
information?
between except that full
Yeah.
information is using
Yeah, right.
right. So but yeah. So I don't know of a comparison.
I think a guy named Enders has done too. It's like
Okay.
Enders 2006 and Enders 2011. He compares thermal and MI and they're comparable if you include the right predictors and if assumptions are met.
Uh-huh,
So,
right on.
good luck with that.
Okay. Other questions or thoughts or like plans for next steps? What are you guys gonna do with all this great information? You mull it over, file it into your toolbox. Okay. All right, happy spring.
Thank you.